I think we now got to the point where I can relax and you can work hard, because now you have this assignment with you. We have got to the point where we learned a few things about optimizing portfolios, how you might selectively invest to diversify, and the primary goal of doing that was to minimize your risk. And doing that exploits correlations between different assets in which you can invest. We learned that it gives you an efficient portfolio that is in the space of mean variance. Not all points are realizable. Yeah? So it makes perfect sense to ask the question, if I want a particular return out of my portfolio, what minimum risk can I achieve that with? Similarly, you can a priori set some threshold on the risk you can tolerate, and then ask the question, what's the largest return I can get out of this portfolio in order to keep my income or my return high. So maximize the return constrained by taking a particular risk position. Okay. So from that we now have this little piece of assignment you have to do. I can so we don't have lab sessions where I have organized demonstrators to come around and help you. I'm kind of thinking that's needed for people younger than you. If you are 30 students, then I'll do this for first semester. I think you can do this entirely on your own. But tomorrow afternoon, tomorrow is Wednesday afternoon, and Thursday morning I will be in my office, building 1. If you are struggling or if you haven't got started, you can drop by and ask quick questions. Yeah. So this, because I want to be absolutely sure that everyone gets started. And I think once you all start, then different people may run at different speeds, maybe. But my job is to make sure that everyone gets started. Okay? So tomorrow afternoon, Thursday morning is for this. You can randomly drop by, but if you drop me an email, I'm dropping by, that increases the probability that I will not go away. Okay? Is that all right? I'll drop an email to everyone as well if you're not here, the people who are not here. I want to make a couple of points about the work you're doing now. One is that we normally work with returns on asset prices. So we are using these stocks as a way of investing and seeing how much money we will make. Yeah. So it is very common not to. It's not. We don't work with the actual value of the stock price as you download from the exchange. You work with the difference time series. This difference is usually and best expressed as a ratio. So if I invest a certain amount of money today, tomorrow it might have gone up by a little bit. So what's the percentage increase is what I would calculate. Yeah? So I would difference the series and normalize by the current price. Okay, so that's the time series, and that's the data on which I'm defining this normal distribution. Okay? And you know that's the way, for example, interest rates are defined as well. So we want to take the price series. Yeah. And if at some point you have at time t minus 1, and if you have s of t minus 1, then my return at time t I would write as ft minus s minus 1. Yeah, something like that. Obviously, you can multiply by 100 and call it a percentage, but this ratio is what we normally work with. When you do that, sometimes you can run into trouble with real data. In real data, there may be missing elements. Sometimes the stock may not have been traded, and you are given a 0 value there. Yeah. So if you have a 0 in there, then of course dividing by 0 creates problems. You just have to watch for those. Yeah. So again, whenever you get real data is always messy. So when you touch real data, you have to be cautious about such things happening. Yeah? So that's the first point I wanted to make. The second point you need to be aware of is when you do the index tracking, we have, okay, so we have the index, those levels, yeah, or the return on the index. I'm going to to match this as a weighted sum of a small subset of stocks I have. So the small subset of stocks I have, I'm doing that. So I'm going to get that as a weighted sum of these. Yeah. So you can easily imagine that if I had a time window of T, say 100 days, and if I had 100 of these stocks, then I can match this perfectly. Yeah? As long as any of these is not perfectly correlated with the others. With me, I can find a set of weights that will weight them up and match that perfectly. Okay? So the choice of the time window during which I do this matching becomes important. So I would of course like to have a big enough window during which I learn this matching. However, when you take a big enough window, it may well be that the relationships might change. Some stocks that are in the market might do so badly with respect to the index, they have become useless. So that compromise between taking a large amount of data to get accurate estimation and taking a small enough data so that you deal with, you escape from non-stationary behavior is an inherent compromise we can't walk away from. This always happens. Okay, so there has to be in practice judicious choices made, possibly based on outside knowledge, possibly based on techniques like cross-validation. You would want to make such decisions. Okay? And you would expect the error between that one and a weighted sum of this one to monotonically go down on the training data as I add more and more functions. As I add more and more stocks, as long as I hit the number of stocks that's the same as the window length, I would get zero error. Yeah? And as I add more and more stocks, I can approximate the target better and better because my model is getting better and better. And on the training data, I would reduce the error monotonically. Okay? But that is not what we really would want. We would want to evaluate the performance of what we are doing on some unseen data. Okay, so you might take a small window, do this optimization as you grow more and more functions, and evaluate how well it's doing on some unseen data. And then what you would expect is on that unseen data, error might kind of go down, it might stay flat, it might even deteriorate, diminishing returns might hit. Okay? And this is why this is part of the reason why instead of grabbing data from 100 different stocks, I said stop at about 30. Take about 30 stocks. The other is if you download 100 stocks data, then the chances of finding zeros and missing values, everything becomes higher. Yeah? So with about 30 stocks, you should be all right. And this kind of phenomenon, that as you increase the modeling power, your performance improves, it hits a plateau and worsens beyond that, is very common. You will find this in many, many different applications. So people do all sorts of things like predicting whatever target from a very large number of data that they have gathered, very large number of features they have gathered. Yeah. So you might think the more features, the merrier. All that happens is the more the features you use, it's better and better at approximating some training data that you have with any algorithm. But outside the training data, in out-of-sample data, performance will very often have that kind of structure. Okay? So if I think of performance, it could be like go up, stay saturate, and then go down. I'm trying to plot error here. Is that kind of clear? It looks fairly obvious when I draw a sketch like this, but I think you can see that when you do this task. Yeah. And I'm hoping that it's not only useful in this exercise, but it could be useful in other things you might do in life. Okay, so that's 2 points. There was a third point. The third point is where I left you on Friday to do with some assets and a risk-free interest rate. And we said the corresponding covariance matrix was going to look like that. Some C1, not. So on Friday we looked at this kind of a structure. Yeah? And I threw this into the efficient frontier finding program, this 4 asset portfolio. And in that 4 asset portfolio, one was risk-free, that is money invested in a bank. Okay? If we compare this one's performance against the 3 risk-free asset portfolio, we can do this one. On the same space, I can take, let's call that M, C1. So this whole thing, let's call it C. Let's call that M1, and then we'll take M. Okay? So M and C plugged into a efficient frontier finding algorithm produced for me a line like that. I can also ask what's the mean variance performance of just the subset of the risky assets in which I'm going to invest. Okay? So there are a couple of things we can note. Okay? And there are a couple of things that I consistently observe, but I haven't managed to prove that that's true. The first thing I've not managed to prove to be true is that y should be a straight line. Okay? And if I manage to figure it out, I'll tell you, I can't find this in the books. The literature I read has this line, and they assume this is true. I haven't managed to prove this, but if you can prove it faster than me, I would like to know. Why is this a straight line when I have one asset on which there is no risk? Point 1. The second point is this portfolio with M and C will have a point here. This we can understand. Yeah. There is a point at which I can have a particular return with 0 risk. And that is putting all my money in the bank. Okay? So in the resulting portfolio, I will have zeros corresponding to the stocks, and I will have all my money 1 in the bank. Then I have 0 risk, and the return is just the same as the risk-free interest rate. Yeah, so this anchor point is clear. Okay? On top of this one, if I now draw the efficient portfolio of M1, C1, books say that it will touch this line in 1 point. Okay? And this we can understand why without working with algebra. Because if we think about this one with M1, C1, are you happy with what I'm drawing? That's my efficient frontier with only the risky assets, only the stocks, yeah, which is what we have been drawing so far. So this efficient frontier, any point I'm on is a unique solution in terms of the weights. For any point in that frontier, I'm achieving that by solving a quadratic programming problem. In a quadratic programming problem, the error is convex like this, and it has only one minimum. Okay, so that minimum I find would be unique. So if you tell me here's a particular portfolio I have chosen, I want to be on this point, then there's a particular way, proportion at which I have to invest to achieve this point. That will never the same as a combination of weights I have in mind to achieve this point. Yeah, so any point of this is unique. Okay? So in a point, so now let's look at this point. This point is on the efficient frontier of the 4 asset problem, as well as on the 3 asset problem, leaving out the risk-free one. Okay? So this point can only be realized by investing all your money in the risk-free, in the risky assets, and putting 0 in the bank. Okay? Now, if this line were to cross this one, then there's a chance it will cut it in 2 places. If it cuts it in 2 places, then you need to have 2 solutions for investing with 0 money in the bank. Okay? And that is not going to be possible. We know the solutions are unique. So that would mean what we read in textbooks of this nature is correct, that without the risk-free asset, we will have an efficient portfolio. Okay? And the efficient portfolio of this one coupled with the risk-free asset will be this line, which will I think we can show this more formally because this matrix has a nice structure which has zeros in a column and a row. We should be able to work that algebra out and show out what I'm saying very formally. I'm not doing this now. What can we now say? We can now say that if I have some money and I have these three risky assets in which I have a chance of investing, I also have the opportunity to put some of it in the bank in a risk-free investment. Yeah. If I'm here, I put all my money in the three assets. Sorry, the three stocks. If I'm here, I have put all my money in the bank. I'm not investing in any of the risky things. Okay? And I can choose many different operating points here by balancing out how much I put in the stocks and how much I put in the bank. Okay? So that's something I can do. I can achieve any of these points. So you can imagine why that is so by looking at, say, take a line like that. How would we interpret that line? If I put all my money in the risky assets, that's the minimum risk at which I can get this reward. Yeah? But it is possible to reduce the risk further and still get the same reward by moving a small amount of it and putting in a fixed deposit. Okay? You can ask the same thing the other way around. If I go up this way, when I can tolerate a particular risk, if I have to invest all my money in the risky assets, that's the best return I can get. Yeah? I can move a little bit of that money. I have the leeway to move a little bit of that money into a fixed bank deposit and get a little bit more at the same risk. Yeah? So those are ways in which you can interpret this. Now comes the, so over here, that's where all the money is in the three risky assets. Any of these points, I'm taking a little bit of money out of that and keeping in a fixed deposit without any risk. Okay? So now here is the puzzle for you. What is that point? What would I achieve here? The graph says I can go beyond investing only in the risky three assets, yeah, and gain more, of course, at a higher risk. And that's worse than, or that's, well, depending on how we look at it, in terms of my greed, that looks better than, in terms of my, well, to stop that, in terms of my risk, that looks better than what I can achieve just with those three assets. Yeah, what does that mean? What would that intuitively mean to you? Let's work a different way. Over here, the amount of money I put in the bank in risk-free investment is 0. Yeah? I would walk down this line. I would save more and more in fixed deposit, avoiding the risky stock market. I come here, all my money is in fixed deposit. I've completely avoided the stock market, but my return is very small. Yeah? I go up and up. I put more and more of my money into the stock market. I've exhausted all my money in the stock market. Then I start borrowing. Yeah? Then I start borrowing at risk-free interest rate from someone and invest it in the stock market. Yeah? So it is of course risky, so I'm going that way. My greed is better satisfied, so I'm going upwards. Yeah? So I can keep walking up this line. Yeah? So you borrow to leverage an investment would be on that line above. With me? And of course it will be that at a particular risk, yeah, because you are risking everything that you are going to this one. Because somebody has let you borrow to invest in the stock market, you are gaining with me? And this observation leads to what's known as a capital asset pricing model. We'll look at that a little bit on Friday. We'll look at that on Friday and then move to the next topic of derivatives pricing options, contracts, and so on. Okay. So where we are now is we learned some basic principles of optimizing and deriving this sort of thing. Yeah, and we looked at this idea that came in from 1952 from Markowitz's portfolio theory, And then we have here. We looked at a couple of recent papers on the same thing, which are Brody's paper. You are implementing some of these, and this Lobos paper, which is about including transaction costs into the optimization process. Okay, so to me, this is about a third of what I wanted you to learn in this course. Yeah, the third of the topic is on portfolio optimization. We started with the basic principles. We looked at some very recent results, of which one you are implementing, the other you're going to read up to the point where there is a difficult set of equations. Okay? Is that kind of clear? Any questions? No? Is that clear? Okay, so you can carry on with the lab work or the first assignment. I think I've set too generous a deadline, at least from my perspective. You will never agree with this. But we start learning derivatives pricing on Friday. And another lecture, then I will be able to give you the next task to do. Okay? Yeah. Oh, that is good. Because it's simply, I mean, that I wanted you to look at that paper. But when they drew it but price is the same. Yeah, the idea is still the same. Yeah. I find it more convenient to think of it this way than that. Many reasons also use this graph. To me, I can think of, I want to have a this one is the other way around. Yes, I agree. Yes. Yeah.
So the first value is.
Yep. Is that what?
Yeah. So this is minimizing risk. So first value is.
I'll just
maximize. So that's the last one. The last one is maximize gravity.
So the issue with short-term investors is one stock. One with the No.
It very much depends on how they interact with each other. So using the box as the design says
Well, yeah, it's sort of on the sense.
so. It allows
Should be something.
what are you talking about?
So you're what?
Oh wait, increasing the number of stuff?
So it's just saying,
How many are you choosing out of?
I would say each time I choose, each point.
6 different ones.
So this was the subset.
It doesn't make sense to me.
No, it doesn't. Shot ratio is actually deviation variance.